An Introduction to Set Theory and to Philosophy and Methodology of Mathematics and Computer Programming by Jan Plaza. Section 1.3, an overview, equality of sets. Here is another axiom of ZFC, the axiom of extensionality. For every u is a member of X if and only if u is a member of Y, implies that X equals to Y. So we understand this as follows. If sets X and Y have exactly the same elements, then they are equal. Some comments on this formula and related formulas. Imagine now a formula like the axiom of extensionality, except that the implication goes in the opposite direction. So this would say, if sets X and Y are equal, then they contain the same elements. This formula actually results from the axioms of equality in logical axioms. And combining the two formulas, we obtain an equivalence. Two sets are equal if and only if they have exactly the same elements. So two sets are equal if all the elements of X are also elements of Y, and vice versa. This will be actually an important property used in proofs of equality of sets. One more comment. The formula, the way I wrote it, involves three variables X and Y. Three variables in a formula are understood as universally quantified. So this is really how we understand this formula. Let us think about corollaries to the axiom of extensionality. We previously proved, using the axiom of pair, that for every elements x1 and x2, there exists a set containing x1 and x2. By the axiom of extensionality, we now know that such a set is unique. Also, we know that for every object x, there exists a set containing exactly x. Now, by the axiom of extensionality, such a set is unique. So the axiom of pair guarantees existence of a set with elements x1 and x2, or existence of a set with the element x. But uniqueness of such sets is guaranteed by the extensionality. Given that now we have existence and uniqueness, we can introduce notation for such sets. A set containing exactly element x will be denoted in this way, and this is called the singleton of x. Given elements x1 and x2, the unique set containing x1 and x2 and nothing else is denoted in this way. So we list the two elements with a comma in between, and the entire thing is surrounded by curly braces. And the second set is known as the pair of x1 and x2. This shouldn't be confused with ordered pairs, which will be introduced later. This is an unordered pair. Some examples and comments on the axiom of extensionality. I can claim that the pair of 1 and 2 equals to the pair of 2 and 1. Indeed, the two sets contain exactly the same elements. The only elements of the first set are 1 and 2. The only elements of the second set are 1 and 2. So by the extensionality, the two sets are equal. When I form pairs, nothing prevents me from taking the same element twice. So it is legal to write a pair containing 1 and 1. However, I claim that such a pair is equal to the singleton of 1, and this notation will be preferred. Why does the equality hold? We can notice that the two sets contain exactly the same elements. The only element in the set on the left-hand side is 1. The only element in the set of the right-hand side is 1. So the two sets are equal. What is the importance of the axiom of extensionality? I will give one example. This will assume that we know about arithmetical operations, about polynomials, about roots of polynomials. If such knowledge is available, I can define a set. The set of all roots of the equation x minus 1 times x minus 2 equals 0. From the form of this equation, you of course recognize that the roots are 1 and 2. By the axiom of extensionality, the same set could be described as the set of all positive integers smaller than 3, or the set containing 1 and 2, which also is written in this way. All these phrases denote the same set, and this results from the axiom of extensionality.